Hey guys, welcome back. We got day 6, the mole and molar mass. All right, so the mole. The mole is the SI unit of substance. All right, we need it. We need the mole because we live in the macroscopic world, right? And we can see these things, right? We can see grams of things and kilograms of things. However, we're measuring single atoms and molecules in the microscopic world, which we can't see. Right, so since we can't see one argon atom that weighs 6.63 times 10 to the 23rd grams, we needed to see 1 mole of argon atoms, which is 40 grams. We can see 40 grams of things. We can see 40 milligrams of things, right? But 40 AMU, we cannot see. All right. Now notice this 40 AMU is the same number on the periodic table as the 40 grams. That's coming into play. So your mole is an amount of any substance that contains the same number of elementary entities as there are atoms in exactly 12 grams of carbon-12. So what is carbon-12? Carbon-12, all right, it's the same thing as carbon-12 there, all right? And carbon has 6, so 6 protons, 6 neutrons, and 6 electrons, all right? This number is Avogadro's number, right? So it's Avogadro's number. And it is 6.022. We'll use that the most, but it's 6.02213, right? 6736 times 10 to the 23rd, which is a very large number, all right? I mean, if you think about that, that's huge. 23 zeros. That's quite a lot of zeros. All right? And so it's a counting number, like a pair is 2, dozens 12, scores 20, right? A gross is 144. This just happens to be large. So if you look at that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right, is that right? 3, 6, 9, 12, 15, 18. I think that's right? That's how big that number is. It's a huge number, okay? So now, are there a mole of softballs in the world? Probably not. Are there a mole of water molecules in the world? Absolutely. There's many moles of water molecules. All right? Okay? And we're just going to count it. So just like if you went to a donut shop and said, I need 3 dozen donuts. We know exactly how many individual donuts that are, right? That would be 36 donuts because a dozen's 12, right? It's no different. So if I need 3 moles of water, we know that we have 3 times Avogadro's number here, right? Which a lot of times we'll abbreviate as NA for Avogadro's number. But I have 3 times that number of molecules of water. That's it. That's all the mole is. So 6.022 times 10 to the 23rd. All right? And the reason we do that is a molar mass. Right? Because we can't count individual atoms and molecules and formula units and whatnot, we need to weigh things. We count by weighing. Not much difference if you go to the hardware store to buy screws or nails. Right? You get a pound of nails, 2 pounds of nails, 5 pounds of nails. You don't get number of nails. They count by weighing. Now, they know you're going to get pretty accurate number of nails. In 5 pounds of nails, the size of the nail, the diameter of the nail, you're going to be pretty close to having the exact same number of nails in each box. All right? You might be off by a little bit, depending on how they measure and how fast they're doing things, but they're pretty consistent. All right? We're doing the same thing, molar mass. Now, atoms, technically atoms have an atomic mass, molecules have a molecular mass, or molar mass, and ionic compounds have a formula weight. They're all molar mass. All right. So if you look at the periodic table, titanium, my titanium here is 47.88 or 47.87, depends on your table. Okay, I use 2 decimals, right? So for example, fluorine is 18.99843 in the periodic table I'm looking at in my office. All right. I don't need to write all those numbers down, sig figs. A lot of times I'll do 2 sig figs, which would be, or 2 decimals, 4 sig figs, which would be 19.00 for fluorine. That's it. Right. Some other ones, like copper. Copper is 63.546. So I would make that 63.55 grams per mole. All right. That's how I would do it. All right, with 2. Compounds. All right. So we look at compound. H is 1.01 and O is 16.00. If I do 2 decimals. Well, there's 2 H's. So that's 2.02 plus your 16.00, right? So that would be 18.02 grams per mole for water. That's it. That's all this is. So now if I have measuring out water, if I get 18.02 grams of water, I know I have a mole of water, which would be 6.022 times 10 to the 23rd molecules. All right. Okay, that is the molecular mass. All right. Now, ionic compound NaCl. Na, right, is 22.99. Cl, 35.45. Add those up, I get 58.44 grams per mole, which is the formula mass. Some call it the formula weight. However, both of these are molar masses. So if you just say molar mass, same thing, okay? A lot of times on a bottle, so if we're looking at a bottle of sodium chloride from the lab, and a lot of times they'll have a FW on it, right? The formula weight, FW, and that would be 58.44 grams per mole. So a lot of times they'll put that right on the bottle. And so you'll see FW, formula weight, 58.44. All right, so in general, mass divided by molar mass, that would give me moles. Right? And so what's the point of this? This is what we use, this is what we measure, and that's our ratio. And the reason we're doing this is not to like, oh, we just wanted to give you guys an extra step. The reason we're doing this is because we weigh things to count them. Because these compounds, these molecules, all these atoms, they react in a particle ratio, not in a mass ratio per se. So like if you're a baker and you're really good at baking and you weigh out your stuff, those are already the mass ratios that we know. And you know you can, as long as you do the same to everything, you're good. So if you wanted to double the recipe, you double everything, it should work. If you wanted to half it, right? You can half it and it works because you have the right ratios already. Okay, but you can't do 1.25 times the amount of flour and 3/4 the amount of salt and 4 times the amount of sugar, and it's just not going to work out, right? Baking is very precise, right? And if you're a serious baker, you know that. Okay, So now we have, in this nice graphic here, all right, we have something we measure. This is what we measure in, right? This is our ratio. And atoms and particle is how they interact. All right? And so a lot of times we are going to measure the grams and calculate with moles. A lot of times we will not go to atoms, right? So there's just, it's not worth it because I can just work in like dozens. Like that's the chemist's dozen, you might have heard. We're just going to work in the moles. So we're going to measure in grams, work in the moles, okay? And so grams, right, just like this general relationship here, all right, you divide by the molar mass, we take the grams, divide by the molar mass, get moles. When we have moles, when we go back to grams, right, we multiply by the molar mass, okay? And then Avogadro's number is over here, right? And so if we have moles and we want to go to atoms, we multiply by Avogadro's number. If we have atoms and we want to go back to moles, we divide by Avogadro's number. So that's your general relationship, all right? And again, all this is so that when we measure something, because again, chemistry, we're going to measure, we need amounts, so we know what to predict, right? Just like if you're having a cookout, you need to know how many hot dogs, hamburgers, or whatever you're cooking to make. And you don't want to make 5 times as much, and you don't want to make 5 times less. You want to make the right amount. Same thing when we do chemical reactions. So let's put it to practice. Now you would need your periodic table. So you need the periodic table. So if you have your periodic table, you need it, right? You do not need to memorize anything on the periodic table. Like, oh man, I need to know the molar mass or the molar mass of hydrogen atoms. Nope, you don't need to memorize that. You can always use a periodic table, okay? What is the molar mass of hydrogen atoms? Well, if you look at your periodic table, you notice that it's got 1.01 grams per mole to 2 decimals. There are times if I need 4, so that's 3 sig figs. But I can get away with 3 sig figs because if I'm going to scroll back up to water here, right? If I add, right, over here, and I have, right, 1.01, 1.01, and 16.00, I get 18.02, right? That's 4 sig figs because when we add and subtract, I get to keep the sig figs as far as right as possible, right? So I get to keep the 2 decimal places. So I have 4 sig figs. Having more is not going to matter, right? If I use 1.008 plus 1.008 plus 16.00, right, I get 18.016, right? To 4 sig figs, that's 18.02. So, right, do I need 5 sig figs? I doubt it. Okay, but however, sometimes I will need 4 sig figs so I can do 1.008 if I'm just doing hydrogen. So sometimes I'm going to use 1.01 more often than not, but there are times where you'll see me use 1.008. If I ever need just hydrogen and I need 4 sig figs, I will use that. Okay, so it depends on what you're doing. What's the molar mass of hydrogen gas, H2? Well, it'd be 2 times this, right? 2.02 grams per mole. All right, H2, it's 2 times the 1.01. So far, so good. Molar mass of carbon, right on the periodic table. Carbon is 12.01 grams per mole. What's the molar mass of carbon-60? That's one of the forms of carbon. Well, that sounds fun. You have 60 times 12.01. So 60 times 12.01, 720.60 grams per mole. All right? Okay, because I got 4 sig figs and carbon-60, that's an exact number. There's 60 atoms there, so we can keep all those numbers. Molar mass of oxygen, right? A lot of times when we say this will be O2, and so it would be 32.00 grams per mole. All right. So there are times where we use 16. There are times where we use 32. All right. Number 6. How many moles of carbon atoms in 60 grams, it should say of carbon? Well, if I start with my amount, so we look at this, highlight, 60 grams is my amount, and the question is, how many moles? So if we start with our 60 grams of C, on the bottom has to be grams of C. So that's from the periodic table. 12.01 grams of C is 1 mole of C. So I'm taking 60 divided by 12.01. Now, I'm just going to do 60 divided by 12 because I only have 1 sig fig. And so I get 5 moles of C. All right. Number 7. What is the mass? Again, what is the mass? And we have 7 moles of N2. So 7.00 moles of N2. On the bottom, all right, 1 mole of N2, right? And then on top, well, molar mass N2. That's 2 times 14.01 for nitrogen. All right, and so that would be 28.02. And so if we do that, I get 196 grams of N2. All right, and since I have 7.00, I get 196 grams. I get to keep all 3 of those. How nice. What's the mass of 3 moles of water? So we got 3 moles of H2O. All right, 1 mole H2O on the bottom. And we know water is 18.02 grams H2O, right? Again, that's 2 times hydrogen of 1.01 plus 16. And so that turns out to be, what, 54 grams? However, we only have 1 sig fig, so that's 50 grams of H2O. All right, and those sig figs matter. All right, because do I have exactly 3? I could have a little bit more, right? Think about the measurements you do when you're adding water to things. It says, oh, 2 cups of water, and use that Pyrex measuring container or whatnot. All right, is it exactly 2.000 cups? Probably not, right? Okay, and so that's where we get the sig figs come in. How many moles of methane are there in 64 grams of methane? All right, so I take my 64 grams of CH4. If you notice, we're going the opposite way. So methane, all right, 12.01 plus 4 times 1.01. So that looks like it's what, 16.05? So we have 16.05 grams of CH4 in 1 mole. So 2 sig figs, 64 divided by 16 would be 4. All right, atoms. Number 10. We have 25 grams of gold. 25.0 grams AU. All right, so our amount is the same, but our question is how many gold atoms? Atoms. All right, so now we know that the molar mass of gold, 196.97 grams of AU, is 1 mole of AU. And then we know 1 mole of AU, 1 mole of gold, is Avogadro's number, 6.0 0.22 times 10 to the 23rd atoms. If we do that, I have 3 sig figs, so I think I get 7.64 times 10 to the 22nd gold atoms. Now, I want to point something out here, because this happens to be on top, so it usually doesn't matter. When Avogadro's number is on the bottom, right? So if Avogadro's number right here is down here, be careful with this in your calculator. Make sure you're using the exponential numbers correctly, all right? Okay, because I've had people give me answers that are 46-ish orders of magnitude off because of how they're using their calculator. So be careful with Avogadro's number, especially when it's on the bottom. All right, last one. How many aspirin molecules are there in 800 milligrams of aspirin? All right, and so if we have 800 milligrams, C9H8O4. Now, some of you can just do that in your head. If you wanted to, or you could write 800.0 times 10 to negative 3 grams, and that would work as well. What we're going to do is write down 1,000 milligrams of C9H8O4 is 1 gram of C9H8O4. And if you notice, I'm keeping the chemical formula there. All right, this is just good note-taking housekeeping, so to speak. All right, so we have no, like, what's going on here? Where's this numbers come from? You know exactly what it is. Now, molar mass. 9 times 12.01 plus 8 times 1.01 plus 4 times 16. So I think the molar mass of this would be 180.17. So 180.17 grams of C9H8O4 is 1 mole of C9H8O4. And then we want molecules. We know that 1 mole of C9H8O4 is Avogadro's number. And so if I do that math, I believe we're going to get 4 sig figs, 2.674 times 10 to the 21th C9H8O4 molecules. So there we go. That is the mole and molar mass. Hopefully that works for you guys. Let me know if you have any questions, and we'll see you next time. Take care.